6 from YUMIN Primary School. In this lesson, we will still be at Electromagnetic Dynamics, Chapter 1, Electric Field and Gaussian Law. For the past lessons, in fact, almost all of these, we'll be saying Chapter 1 will learn the Gaussian Law, but we haven't even learned it yet. And now is the time that we will really start studying about the Gaussian Law. But let's put first things first. Let's recap what we have learned before. So, in the last lesson, we have drew something like about their relationships from the things that we have learned. Okay, I'm going to draw that out again, but I'm also going to change it. And let me tell you why I need to draw this out, because after when I draw this out, I would relate this to different methods of calculating the things that we need to the Gaussian law. Okay, so let's start this. Very important thing, the F vector. This is the Coulomb force. And for this part is the 1 over 4 pi epsilon naught times Q1 Q2 over R squared, like this. So this is the Coulomb force. So what can we relate this to? There is a relationship between some of these. Like, let's see, how about electrostatic field strength? So this electrostatic field strength is 1 over 4 pi epsilon naught times Q over R squared. This thing, so F vector to E vector. Now what is that? F to E, we have E vector that is equal to F vector over Q. Then E vector to F vector, simple, using the same thing, times. But what is this called? Okay, well, let me tell you, this is their definition. Okay. Next, F. Does it have anything else that it is related to? Well, of course, yes. We have the work done. And for your information, E vector, or the E, the electrostatic field strength, can be called the Coulomb field strength or specific force. Okay, so let's see, this work done here, F vector to the F, that is integration. So this is the W that is equal to integrate along this line. Then we have F vector dot D R vector, like this. Okay, then how about the other way around? Well, the other way, you might just think, well, it is differentiation, simple. But let me tell you this, it's actually different things. Let me tell you what is one of these. Have you heard of Hamilton? Then this is the Hamiltonian mechanics. So that means for these we'll learn more about them in the future. So Hamiltonian mechanics, we also have Lagrangian mechanics. like this. Or how about another way to relate that? How about let's go from the work done. Work done, we get the specific work done. That is the electric potential. So W to V, that is V that is equal to W over Q. Then V to W, same thing. W that is equal to Q times V. Then how about others like E and V together? E and V together, we have verified this before. Yeah, we have verified this before. So let me just tell you what is it. E to V, integration. V that is equal to integrate along this line. Then we have E vector dot dr vector. Then the back, we have the gradient. That is actually differentiation. Then how about I write this as a negative delta V? So del is decrease. Delta is, well, increase. Okay, so now we have this thing that looks like this. We have this direction, also the specific work done. So this electric potential, we can also write it as 1 over 4 pi epsilon naught times Q over R, like this. Then, the most important things are that we calculate these two. So we calculate the E and the V. Calculating E and V. Most commonly asked in electrical questions. Okay, so let's see. How can we try to find the E? Well, for E, we can be summing all of them up. Maybe. Or if you don't want to sum all of them up, anyway, here's a vector. If you don't want to sum all of them up, you can find in which directions. Like EX, you can add all of them. EY, add all of them. Or if you don't want this, but some cases you must use this. But there are other cases where you don't really have to use this. Just integrate. But this integration, what I'm writing now is just the simplest forms. Now, what happens after you get these? So let me tell you what can happen. X, Y, Z. E squared is equal to square, square, square. According to the Pythagoras theorem, we get this. Okay, so this can be a method to find the E. Sometimes, wait, E has components, but electric potential doesn't have the components. So, but you can use integration to straight away find it. E, you can also use integration to straight away find it. Sometimes you might want E first find, then change it into V, like that. Or sometimes you might want V, first find, then change it into E, sometimes like this. Okay, so at this part, let's just say we have this random plane, because this can be for any. So this random charged, okay, it can be a particle, it can be an object. And then we have this x-axis, and on it there is a point called P. Now let's see, if we start from E, where do we start integrating? Of course, on the inside of this object or on that particle, then V. Well, obviously also inside or on it. Then after that, when we change E at first inside, then we'll change it into a V. Then that will become on the outside. Okay, then V change it to E. It is also on the outside of this, you can call it the object. So it is like this, outside. But they're all methods to calculate this E and the V. But there is another easier method, because this is a good method, but not the best. Now, what is that best method? So let me tell you now. That is what we're mainly focusing on for this lesson. The Gaussian law. We finally came to this. Or the Gaussian theorem. Okay, so at this part, let me write what is it like above here. Whoops. Okay, let me just write this. Okay, so at this part, first let's try to understand these part by part. So this stands for the surface integration. Then inside here, what do we call that? This E vector dot ds vector. Well, for this is something that we call it the flux. Now, what is this flux? So this flux, okay, let me write here. So right now, let me explain a little bit more about this flux. So this flux, you have E vector dot d a vector. So at first you might think as vector, well, it might be okay, but well, actually we prefer to write a vector. Okay, so let's see. At first you might think area, how could it have a direction? Well, area, it actually does have a direction, it's just depending. For this thing, do you assume that way is positive, this way is negative, or other ways? And even if you work out, you get a different direction, it's still okay. That at first was just an assumption. Okay, right now, can we just like break the A vector down or something? Well, we can break the A vector. E vector stays there. The A, there has the times. That vector would now need to go somewhere else. Well, you leave that to the n vector. Now, what is an n vector? So things, they have a normal force. And this normal force, that is also a unit vector, is called an n vector. Like this. Other ways to change it. We also can change it into E vector, dA cosine theta. This method also possible. Okay, so cosine theta, or you might want to change the order. So that, wait. So that will become like this. Okay, so it is now something like this. Okay. So at this part, are you all clear so far? So let me give an example of this flux using water flow. Okay, let's say we have this water flow here. It's a river. So this is the river. Then let's say this river, we only want this part and this part. Okay, so let's just say we have this part, and then it flows at a speed of v vector. Well, because water flow, they do have a direction, it's true. Let's see. It is given a limited time. Let's try to find out this length. So this length, vt. Because we only want the speed times its time. For that, we can call it the length. Okay. Now we have this length. What's so useful about that? Let me show you. Let's say we take this little piece out of it. Then you cut it. Let's just say it's stopped. You cut it, and then you realize it is like this. So that means at this point, when you have something like this, we can call this cross-section area A. We're going to call that A. Then A times L. What does that mean? So it is this whole cuboid. When you take it out, it looks something like this. It's a whole cuboid. This volume is AL. Then what if I want to divide it by time? That is the volume of this little tiny bit. Like this. So L is V times T, then that means this will be A times V. But V, what if I add in this vector? That's a problem. That means you need a dot. A vector, but where did that A get its vector from? Well, it's actually pretty much the same. You have an N vector. So for this N vector, that is the normal unit vector times the A, and that's how you get your A vector. So let me just tell you, for this A vector is equal to A times N vector, like this. Now how about what if I go back to the flux? Now you have to imagine this water is completely frozen in winter. It cannot move. You have to push it to make it move. Now this flux, it's just like this force acted on this area. But then this area also have a vector. And let me just tell you, for this part, for more information, you have V times A. It's the same. Okay, so this force, and you times this A. This is the flux. Then this is the flux. You can say, I throw one thing go through this area, like the force, and this area, like you can say, I go through this how many times? Okay, that can be one of them. So let's come back to this Gaussian law. So this Gaussian law, let me read this part. So, surface integration or the flux. That means like for something you feel, okay, we got all the flux. Then that is equal to, now this rho. What is this? Okay, this is the density. But what kind of density? So this would be, in this case, our charge density. Like this. Then how about that dV? Well, that is just a little bit of the volume. Then triple integration to add all of them up. So for that, the surface integration basically is saying about the flux that we can feel on this thing. It's actually equal to the total charge over epsilon naught. That is quite amazing. Let's give this example. Okay, for example, this is the part that I have. Then let's say this is a charge. This charge inside, I don't know how much in there. Let's just say I don't know how much is in there. But let me feel. The flux must be on all sides. Cuboid is 6 sides, sphere only 1 side. Okay, then that'll tell you why sphere only have 1. Feel. Okay, the flux. I know them. I just get them all together, add them up. Then that would be equal to the total charge over the epsilon naught. Isn't it amazing? You can actually know how much charge is inside when you don't know how much is inside. You only need to know the flux. So in the next lesson, we'll learn more about calculating this flux. Okay, then let's see. This is charge density. Because it's the charge density times whatever volume we have. So that means it's the charge, the total charge over the epsilon naught. So I said that I will give the example about a sphere. So let's see this sphere that we have here. Let's just say from its center. The center of course can come here with that E vector. But did you realize they're all the same? If they're all the same, like this is the charge inside the sphere, they're all the same. If they're all the same, then that means it's just, this whole thing is just one-sided. Yeah, it's like that. If you say cylinder, one side, to 3 sides. Okay, so let's see. What if I want to prove something? Let me see, like a sphere. Okay, let's try this. Let's just try this beginning example. Okay, starting with this surface integration as E vector dot dA vector. And then this is equal to, so remove those 2 vectors first. E times dA. Then you have E that you can take it out. Then inside just dA. Now what is that? Well, the surface area of a sphere. Well, we have actually proven this before. I think it's like in calculus. So that is the E times 4 pi r squared, like this. Now what is this equal to? Total charge, Q over epsilon naught. Then wait a second. Isn't this what we have learned before? Just that its positions changed, but it's all right. Did you realize that? It's the exact same. Okay, so this is just one of the examples they're trying out here. This is right. Okay, so for this lesson, the first lesson of the Gaussian law, we can end here. Then the next lesson we'll learn more. Okay, so if you like our videos, don't forget to subscribe to our channel. And this is Electromagnetic Dynamics, Chapter 1, Electric Field and Gaussian Law. First lesson on Gaussian law, very interesting. How did this person think of it? Just the flux on the outside, the surface, is equal to the charge inside over the epsilon naught. Okay, so we'll end this lesson here. And thank you for your watching.